All right, good morning, everyone. It's really exciting to see you all here. We are back in person after a while, after having some virtual symposium. My name is Rada Mihalcea. I'm a professor here at Michigan and also the director of the AI Lab. And we are really very excited to have you join us for our annual AI Symposium. I'm very much looking forward to an exciting day of exploration and learning, and most importantly, of connections between us with our shared interest in this growing field. The AI Lab at Michigan has a long history, more than 30 years. It started back in 1988. Originally with a rather small group of about 4 people who are interested in cognitive agents and computer vision, but eventually it grew into what is today one of the largest AI labs in the country and beyond, with 25 faculty members, nearly 100 PhD students, many master's and undergraduate students, and of course postdoctoral fellows and research scientists. We are really one of the strongest AI labs, consistently ranked in top 10. What sets us apart is not only the long history of the lab and its research strength, but also our very deep belief in the role of diversity. And what I mean by that is diversity across the entire AI pipeline. We believe in diversity of thinking. In order to truly advance this field, with such a huge societal impact, we need people who work in all areas of AI. And in fact, our students and faculty have expertise in a large number of areas, including machine learning, computer vision, natural language processing, robotics, graphical models, cognitive agents, and more. We also believe in the diversity of the data we use to feed our models. Across the board, our faculty are thinking deeply about building models that leverage data and annotations from a diverse group of people, so that the resulting models account for a comprehensive set of experiences, interests, and values, and eventually are fair and not biased. We believe in the diversity of the researchers who are conducting this work. We are, whether we like it or not, limited by our own experiences. And so we cannot really encompass, as individuals, as unique individuals, the full spectrum of experiences that one can have. We really believe that it's important to have people of diverse genders, diverse ethnicities, diverse backgrounds at the table when the big AI decisions are being made. While we still have a long way to go as a lab, we are very proud to be moving in the right direction. Just look, for instance, at who is on our faculty, and you will know what I mean. And last but not least, we believe in the diversity of user experiences. Who are the people who will ultimately interact with our systems? AI eventually will penetrate most areas of life to support us in what we do. And we do need AI that can support every single one of us. Which takes me to today's symposium theme, AI and accessibility. There are very important questions to be asked and answered in this space, and how AI can be used for accessibility, and I'm so excited about today's program. While not the entire program is about AI and accessibility, a big fraction of it is it is. I'm very excited to hear from our wonderful keynote speakers, invited speakers, panelists, poster presenters, and from all of you, the audience, about what you believe is important and what are the next steps we can take, especially in the theme of AI and accessibility, but more broadly in AI. And with that, let me introduce the symposium chairs who have done an absolutely terrific job in bringing us today together to explore these important questions and have really put a lot of work. So today is really what we are all going to enjoy, but they put a lot of work for a long time to make this possible. So I'd like to introduce Professors Joyce Chai and Anhong Guo. Professor Joyce Chai works in natural language processing and robotics, and Professor Anhong Guo works in human-computer interaction and accessibility, and they will tell you more about today's program.
Thank you, Rada. So I'm Joyce, Joyce Chai, and with my colleague Anhong Guo, would like to welcome you to our annual Michigan AI Symposium. And this is our 5th edition of AI Symposium, but it's the first since the pandemic. So it's really great to see everybody here in this room. We have 10 speakers, invited speakers in the program, and 6 of our speakers actually flew in just for this event, so we're super grateful for that. And we also have 4 internal speakers, so you're gonna have a chance to see some of the activities on campus. And we're gonna have 52 posters and demos, cover a variety of interesting topics, so please check them out. Certainly, we have a large group of student volunteers really helping to set things up, and will help you throughout the day with registration, coffee break, and so on. And what's really impressive is we have over 200 registered attendees like you here. So it's not just from University of Michigan. Our attendees coming from nearby universities like Michigan State, Eastern Michigan University, and also nearby companies. So it's really exciting to see this overwhelming interest in AI in this region. The next. Okay, so yeah, we have awesome poster co-chairs Chen and Martin. They have done a fantastic job putting together the poster session, and we have the volunteers. Okay, thank you. So student volunteers, and also several of them are not listed here, many more. And the local arrangements, Aura, Steve, Kim, and Steven, they have done a fantastic job and putting the local arrangement plan. And last but not the least, we have sponsorship from LG Research we're very grateful for their generous support to this symposium. So next I'm gonna pass this to my colleague, Anhong, and he's gonna talk about the program.
Thank you, Joyce, and thank you everyone for coming. For those of you who are just here, please, there are a lot of seats in between and also on the front row. Please come and take a seat. So I will briefly walk through the program for today before we jump into the keynote talk for this morning. So we have 2 keynote speakers, Sonia Chernova from Georgia Tech and also Jacob Wobbrock from University of Michigan. So for the day, we will first have a keynote talk, and then until about 10:40-ish, we will have a short coffee break. And from 11 to 11:40, we'll have 2 invited talks by Professor Sheila Maharan and also Professor Dhruv Jain. And then from 11:40 to 12:10, we'll have 4 lightning talks from Emily, Elvis, Asher, and Shivali. And then we will have a kind of an informal poster pitch session where everyone who is presenting a poster can line up and give a 30-second pitch of who you are, what you're interested in, and what your poster is about. And then we will go outside to enjoy lunch and also our poster and demo sessions. And for the afternoon, we will have another keynote from Sonia, and followed by invited talks by Stella Yu and Wei Hu. And after a brief coffee break, we'll have another very interesting AI accessibility panel with some closing remarks. And we'll also give out some awards for posters and demos. All right, so that's an overview of today's program. Welcome all of you again. We will enjoy a day of AI and accessibility and more. And now we will go into the first keynote. Thank you. So for our first keynote, we'll have Professor Jacob Wobbrock giving a talk on ability-based design. What role does AI play? So Professor Jacob Wobbrock is a professor of information by courtesy, computer science, and engineering at the University of Washington. His field is in human-computer interaction with a focus on mobile computing and accessible computing. And he directs the ACE Lab and is also a co-director of the UW Create Center and is a founding member of the DUB Group, which is a collective of HCI-related research, and also the MHCI Plus Design degree at the University of Washington. He has co-authored over 200 papers and 19 patents, receiving 27 paper awards, including 7 Best Paper and 8 honorable mentions from ACM Chi, the flagship conference in HCI. So for his contributions in accessible computing, he received a 2017 SIG Chi Social Impact Award and the 2019 SIG Access Paper 10-Year Impact Award. He has also received a 10-year Lasting Impact Award from ICMI for his work on gesture recognition. In 2019, he was inducted into the Chi Academy. In 2021, he was named an ACM Fellow for his contributions to human-computer interaction and accessible computing. He holds a Bachelor of Science in Symbolic Systems and a Master of Science in Computer Science from Stanford, and a PhD in Human-Computer Interaction Institute from Carnegie Mellon University. So I also got my PhD there, and fun fact that Jake was a general chair of the Technical HCI Conference WIST that just happened at Bend, Oregon earlier this week. Yeah, so both of us just flew back from the conference. So let's welcome Jake for today's keynote.
All right, thank you for the introduction. I'm really impressed you can all, you can get all these people here on a Saturday morning, including me. I'm 3 hours behind from Seattle, so somehow my laptop's not receiving power. It's always the basics, right? So hopefully it survives the presentation. I don't know why it's not getting power, but if it dies, we'll adapt. Okay, I want to talk to you today about a project, really a theme, an agenda that I've been working on with my students for over about 10 years. It's called ability-based design. And today, because of the theme of the symposium, I want to highlight ways in which AI can make a difference to ability-based design and get you thinking, hopefully, about opportunities that you see for improving accessibility through AI, perhaps in the purview of ability-based design. I am not an AI researcher. I'm an HCI researcher, but I use AI in certain projects, and I'll show you examples of that today. So many of you AI researchers, you're making hammers, and then I pick up your hammer and I hit nails with it. And so you will not see probably any groundbreaking AI research in this talk, but hopefully you'll see inspiring ways that we've applied AI to interesting HCI problems. There's a screen at the hub at the University of Washington. The hub is kind of the student union building. And these screens are spread all throughout the hub. And it always kind of struck me as having an interesting and somewhat problematic word on these screens. They're hung on the walls. They're about arm height. And they look just like this. Does anyone maybe want to guess what's the word that I'm keying into here that I find a little bit interesting? Just. Just. Exactly, just. Just touch the screen. Just touch the screen. But is it really just? There's a little bit more to touching a screen mounted on a wall than the word just sort of implies, right? What do you have to be able to do to just touch the screen? You have to see that it's there. You have to be able to suspend your arm. You have to be able to reach. You have to probably be able to extend a finger, maybe land and lift from the same point.
Maybe overcome your COVID fears.
And right, be willing to touch something that perhaps thousands of other people have just touched, right? Yeah, so there's a lot more to it than just, touching the screen. And that's one of the simplest interactions that we have today, particularly on our own personal phones and tablets, right? We just tap, but it's not always so simple. When we design things, we take ideas, things that started for us as ideas, and we embody them in some way, right? That's really the act of manifesting a design. Whether it's just a sketch on paper prototypes, cardboard prototypes, or high-fidelity prototypes that have hardware or software on user interfaces on a screen, all of those are forms of embodiments. The thing is, when we go from ideas to embodiments, we are bringing certain assumptions into the form that those embodiments take. They may not be conscious assumptions that we make, but we are bringing certain ability assumptions into those embodiments. And the challenging thing is that when we put those in the world, they're meant to be encountered by other embodied people, right? We're all embodied. We can't escape our bodies. And yet, the embodied people who encounter our embodiments may not have the abilities that our embodiments, that our designs assume. And the world can become an exclusionary and rigid place as a result. We can think back to some of the many innovations in interactive computing and question, what are the embodiments, what are the assumptions that these embodiments have brought along with them? So on the screen, I'm showing Sketchpad, the famous interactive system from MIT, Ivan Sutherland, with the light pen on the screen. Next to that, I'm showing the first mouse that was part of the NLS system, of course, famously demoed by Doug Engelbart and Bill English, and the iPhone from 2007. All of these are different interactive embodiments that have certain ability assumptions, right? And we take for granted, in many cases, those assumptions, but that's precisely why we need to pay attention to them, because ability assumptions affect how people interact with devices. And we might do our very best to avoid making certain ability assumptions when we design things, but you can't escape them, right? You can't escape them. You will make certain assumptions. So the question is, where do those assumptions come from? Do they reflect your own abilities, consciously or probably unconsciously? Oh, I can use it, so I built it, so others can use it the same way? Maybe. Or do they reflect the abilities you imagine other people might have? Do they reflect the abilities of some kind of mythical average user? There's no such thing. But we sometimes kind of think that way without being real conscious of it. Maybe you're doing empirical work. That's probably a good step in the right direction. And they're reflecting the abilities of people you've worked with, maybe in a participatory design fashion. That's getting maybe closer to what you're after, but you just can't escape it. In the post-World War II era, assistive technology was really about replacing something you lost. So you lose an arm, we'll give you an arm. You lose a leg, we'll give you a leg. Because the world is going to be what the world is, we're going to fix you. We're going to fix you to match the world. And in a post-war era, when people are returning from battle, if they were lucky enough to return, and they had missing limbs and things, I suppose in a certain way it made sense to think about helping restore what they lost. But this is prioritizing the world over people. It's allowing the world to remain rigid and making people adapt to it. But now we live in an era of computers, and they're supposed to be smarter than a concrete flight of stairs. A concrete flight of stairs can't really change, adapt. It can be supplemented with a ramp, but the stairs are the stairs, and they're made from concrete, and that's kind of what you get. Shouldn't we be able to do better with computers? I mean, they can sense, they can interact, they can adapt, so we should do better. And that's largely what the theme of today is, my talk today. So in this slide, I'm showing images of people still adapting themselves to, in this case, input devices. We have someone using a hand stick with a keyboard. The keyboard doesn't know how it's being used, right? It's designed to be typed on with 10 fingers, right? But it doesn't know different here. In the middle picture, this woman is typing with her feet. There's actually a video of this. It's incredible. She's incredibly proficient this way. And we see other embodiments, people using mice and trackballs. There's a person using a trackball with his chin. Our systems are oblivious to these things, right? They have no idea how we're working with them. We're adapting ourselves to work with them. Alan F. Newell, not the famous cognitive scientist and AI pioneer that you've heard of, Alan Newell, but Alan F. Newell is a Scottish accessibility and assistive technology computer scientist. It gets confusing in the accessible computing community sometimes. He points out everyone has abilities. He says, common sense and observation show us that every human being has a set of abilities, some of which can be described as ordinary and some of which are very obviously extraordinary. He talks about extraordinary human-computer interaction. It's actually a title of a book of his from 1995. Here is a picture that I really like. It was on the title slide you might have seen, of a man essentially jumping and diving to spike a ball in wheelchair rugby, which is also sometimes called murder ball, which is quite a title for a sport. I don't think I'd have the guts to play anything called murder ball. But he's clearly got extraordinary abilities. This is the US national team. He's leaping, he's diving, he's spiking. Extraordinary abilities, and yet he's in a wheelchair, right? And what's the common perception of people in wheelchairs kind of broadly in society? Not this, right? Not these extraordinary athletic abilities. And yet people have extraordinary abilities. Businesses are starting to kind of key into this a little bit. So here's the homepage of Bank of America from a few years back, and there's a section, See Our Abilities. Our employees with disabilities provide services core to our business. Microsoft's Inclusive Design Principles page also acknowledges this, solve for one, extend to many. Everyone has abilities and limits to those abilities. Designing for people with permanent disabilities actually results in designs that benefit people universally. Constraints are a beautiful thing. Abilities are also affected by context, right? We don't interact in some kind of void, right? We interact in context. Embodied people in an embodied world interacting with embodied things. Alan F. Newell had this sketch in his book that I mentioned. It's a little hard to see, so I'll highlight. There's a soldier here. And the point is that even though the soldier in their person may have extraordinary abilities, strength and stamina and so on, in this picture, the sketch is showing that this soldier is stuck in the mud, terrified by fear, deafened by loud booms going off all around them. There's tanks and shells exploding in the background. And yet there's an office desk and a filing cabinet, as if to say that this person trying to interact in an office setting would be severely disabled by the context, right? So context affects all the ways in which we interact and affects our abilities. So we can't ignore context. So when we're talking about abilities and we're talking about ability-based design, as you'll see, context makes a big difference to what we can do. So let's get specific about computing in that vein. In the 1980s, if you were interacting with a computer, it probably looked about like this. What this looks like, I'm showing a picture of a woman in an office typing at a keyboard at an old desktop PC. What does she have here? She has stable temperatures, a stable work surface, controlled lighting. It's probably quiet. Her posture and her seating is stable, right? It's a very controlled environment for her to interact in. Next to that, I have someone sitting on a beach marked today, typing on his laptop that is propped up on his knees. It looks like it might be a cold weather beach. Maybe that's Lake Michigan or something. He's got a hat on. It's probably winter time, but there's sunlight glare on the screen. And his work surface are his own knees, which clearly are not going to be permanently stable like a desk. Think about the ways that interaction between these two scenes is different for the person. It's really different, right? But they're both working on a computer. So if we just think, oh, we're just working on a computer, well, there's a big difference there. What are you actually thinking about how people are interacting? And if we go to even smaller, more portable mobile devices, the context can vary even more. We know from studies in HCI that, for example, just walking has a big effect on how you interact with mobile devices. It reduces your reading speed, it reduces your motor accuracy, it divides your attention. You know, you attend to a smartphone if you're walking for about 4 seconds, and then you look up, hopefully, so you don't run into something, and then you interact for 4 seconds again. You interact in 4-second bursts. That's very different than that woman in the desk in the office, right? Or think about if you've been really heads down writing code, as we've probably all done, and you're just buried in your code. You are not interacting in 4-second bursts. You might be interacting in 4-hour bursts. And then you remember you probably should get up and use the restroom, hopefully. So 4-second bursts is a very different way of interacting. We also have reduced ability to maneuver and avoid obstacles. So we're beginning to adapt the world, or at least kind of adapt the world, or recognize in the world that we need to be aware of how people interact in context, especially when mobile. So here's a sign from Hayward, California. Heads up, cross the street, and then update your Facebook. This is an actual street sign. In Honolulu, Hawaii, you now get a fine if you are on your phone in a crosswalk. It's a $50 on-the-spot fine if a police person catches you crossing the street on your phone. Right on the spot, 50 bucks. In Chongqing, China, they've experimented with different lanes for walking if you are using your phone versus promising not to use your phone. So this is the lane on the left where you can run into each other, and on the right, you know, you're promised to abstain from that. Of course, the irony is if you're on your phone, you might wander into the lane where you're not supposed to be on your phone, so it's not clear that that'll actually always work. In a neighborhood in London, they padded the telephone poles because they had so many face injuries from people running into telephone poles, right? So broadly in HCI, we call these situationally induced impairments and disabilities, or situational impairments for short, because you are impaired, right? You are not fully giving your attention to your environment and all those other things I told you about studies have shown. In Amsterdam, or in a neighborhood near Amsterdam, they've taken to projecting on the ground a laser showing the crosswalk status rather than requiring you to look up. So you know the little white person, or you know the don't cross hand and the white person when you can cross, that requires your eyesight to be where, right? Up. But if you're like this, you're not looking up. And so they said, well, let's put the display for the crosswalk in your periphery where your head is. So we're all walking around like a bunch of zombies like this, right? I don't know if that's really the world we want to live in, but it is the world we live in now. In 2018, which was the year of the most recent data I could get, the Federal Transportation Agency estimated 400,000 texting-related crashes in the United States. 38,000 of these resulted in death. So it gets serious, right? It's not just about knocking your nose against a telephone pole, unpleasant as that might be. Texting while driving is deadly. Okay, so that's kind of the setup for ability-based design and why I think it matters. So what is it? And why does it have, I think, promise to addressing some of these challenges? So ability-based design, a design approach in which the human abilities required to use a system in a given context are scrutinized. So that's calling forth those ability assumptions I talked about. And systems are made operable by or adaptable to alternative abilities. Ability-based design comes from an attitude that we need to focus on all that people can do rather than focusing on what people can't do, a kind of deficit orientation. Focus on what people can do and make our systems do the work of accommodating their users. Make our systems accommodate their users rather than our users accommodate our systems. Were this to be carried out in full, in its full vision, it would result in a world in which anyone, anywhere, at any time can interact with systems ideally suited to their situated abilities, and our systems are the ones that do the work to achieve this fit. So ability-based design is sort of strategy agnostic because we're after that end result, and there's lots of roads that lead to Rome. So it can involve things like automatic ability-based adaptation. I'll show you an example or two of that. High configurability by end users themselves. Ability-specific recommendations, for example. A system might recommend certain things after observing its user. Or a wide variety of ability-based settings, wider than maybe we usually encounter. The point is that systems match users' abilities and that users don't have to strive to satisfy systems' ability assumptions. So there's a visual language by Alistair Edwards that I think communicates this idea. This was also in that same 1995 book by Alan F. Newell. And it's a very simple kind of visual language. So I have a couple shapes on the screen. One is labeled user, the other is labeled system. And in this case, they sort of fit together nice and seamlessly. So the user and the system match. The user's abilities and the system's ability assumptions match, and we go about our happy way. But often that's not the case. So in another example, I'm showing a user shaped like a sort of a triangle and the system with a curved shape, and they don't really fit. So then what? So the traditional approach in assistive technology is to procure an adaptation that the user fits, and then the adaptation essentially makes the user suitable or amenable to the system. The problem is that the system often doesn't know that that adaptation is being used. Now, I'm not saying this has no place. Obviously, there are solutions in this space that are very effective. Nothing wrong with that. This is not a takedown of assistive technology, but I'm pointing out how it's going to differ from ability-based design. The problem with this scheme is that notice where the burden moves. It starts with the system and it moves on to the user, right? The system has a certain set of requirements, so the user has to procure an adaptation to make the user agreeable to the system. So the burden flows from the system to the user. If we flip that burden, we're more in the realm of ability-based design, right? How can the system have to respond to the user? So could the system change? And then the user and the system are again a match. That's the concept in a sort of visual language there. Okay, so we're ideally getting rid of adaptations that have to be procured separately by the user. We're also in a contrast in some ways to universal design, which again, this is not meant to be a takedown of universal design either. Universal design is great and has many, many uses, especially with relatively simple physical products. But we have systems that try to be usable by the broadest range of people's abilities as possible, and that's fine, but then we're, in some cases, not always able to match the user's specific abilities as good as we might want. So we're going to look at a few past projects. Design talks tend to, and sort of design education broadly, tends to I guess, try to educate through examples. It's a very inductive process, right? We have these principles, and then here's a bunch of examples, and we'll learn from those. So in that same spirit, we're going to look at some of these. And I have marked on the slide, where's the AI and where should be the AI? And some of these projects, all of these projects have, I think, some AI in certain ways, but maybe could benefit from more. And as we get towards the end, I'll share with you a vision where I think I'd love to hear your thoughts about where AI could make a big difference. So we've done lots of different projects over the years that I would characterize as having elements of ability-based design in them. And we've begun to see patterns emerge about really how we are working this process through. So I'm going to share just a few here. The first one, which deserves a lot of credit, is a project that I got to be involved with when I came to the University of Washington, and I began to co-advise Krzysztof Gajos, or Christoph, you may have heard his name that way, Krzysztof Gajos. My wife's Polish, so I know how to actually say his name more or less. And he's a professor now at Harvard and has been there for quite a while. But his project was called Supple. Anyone heard of Supple? Can I see a show of hands? I'm just curious. Okay, not that many. So Supple is an automatic user interface generator. I'll show a quick video which will explain more, so I'll just briefly say on this slide what it does. We first issue a testbed of tasks, input tasks, to users. So it's a separate testbed process. We'll come back to that idea later. So there's pointing tasks, some dragging tasks, list selection tasks. We build regression models of people's movement time. And then Supple was a user interface generator that could receive those models to parameterize its search process to automatically generate optimal user interfaces that reduced movement time, that's the cost function, and created custom user interfaces for each person. It didn't have any declarative or heuristic knowledge. It didn't know you had cerebral palsy or muscular dystrophy or Parkinson's or tremor or whatever. It just optimized for your movement time. So, for example, on the left, we see a Microsoft Word font dialog box. And then Supple generated this one in the middle for someone with cerebral palsy, which has big targets and multiple tabs to overcome certain forms of tremor. And then on the right, we see one generated for someone with muscular dystrophy, which has small targets but no tabs, so that the movement distances were shortened, but they were actually fairly accurate. So let's take a look a little bit more with this video about Supple here.
To generate a customized user interface adapted to a person's motor
It's not wanting to give me the subtitles here.
abilities.
Okay, pardon me while I step out of this, and I'm going to go ahead and actually I think I have to turn off presenter view. Sorry. This is I'm going to blame Microsoft on this one. 2 seconds and we'll have it. There we go.
To generate a customized user interface adapted to a person's motor abilities, Supple first collects information about how a person uses a computer. By observing the user perform various basic tasks such as pointing, dragging, clicking, and list selections, Supple builds a model of that person's unique motor abilities. Supple's optimization algorithm then calculates the interface that maximizes that person's speed when using a particular program. How does Supple do in making computers easier to use?
The full video is online if you're interested, but I'll show you some brief results here. So for those of you interested in the technical details, of course, they're spelled out in multiple papers, including an AI journal paper that talks about the optimization process, the cost function. It uses a branch and bound constraint-based search algorithm to find the optimal interface, because obviously the space of possible interfaces is really, really big. So if you want to nerd out with me in the hallway, we can talk more about that. But the results are here on the slide. The ability-based or Supple-generated interfaces reduced movement time, particularly for the motor-impaired group, significantly. The widget manipulation time was really where most of the savings were. There was also a little bit of time saved on the navigation time. So these interfaces were quite a bit more usable for the people for whom they were generated. Error rates as well, not just movement time, because of course speed and errors trade off against each other, were also lower. So we have both a speed and accuracy win, which is hard to get both. Usually you end up with a trade-off in these kinds of studies. Oh, and they were faster and more accurate for people without motor impairments as well. So that's a nice win. Another project I'll share is called the Angle Mouse. The Angle Mouse is an adaptive gain-controlled mouse. So your gain is where you move your mouse speed slider, right, in your control panel. And the observation here is that and these lines drawn on the screen as the mouse moves are just illustrative. So you can see the spread of angles. But as you move towards a target, you initially move in what's called the ballistic phase of movement. You kind of shoot out in the general direction of the target. And the angles that are created if you sample the mouse movement as it moves tend to have a fairly narrow, coherent band of distribution. But then as you get near the target, you make what are called sub-movement corrections around the target. They're very subtle, but if you actually measure this, you'll see it. It's true for all of us. We do this. We shoot out and then we correct. And as we correct, the angle, the distribution or deviation of the angles really explodes. So we can detect that because if you have a motor impairment, getting into the target at the end can actually be quite challenging. Notice we don't know what target a user's headed for, right? That'd be understanding their intention. And we also don't even know, and it's very theoretically hard to know, what are all the targets on a screen. So there have been pointing techniques that try to augment targets, but those are really, really hard to use in practice. They work in test beds where you kind of know what the targets are, but they don't really work in practice. Think about Microsoft Word. What's a target? The space between every character? The margins? If you double-click the margins, you get the margin dialog. A word, paragraph, everything's a target, every pixel's a target. It's not really definable. The nice thing about the angle mouse is it's target agnostic, right? Because it's just looking at the angles, the behavior of the user, it doesn't have to know anything about where a target might be. So what we do is as the angular deviation spikes, we drop the gain. What does that do? That magnifies the target in motor space. Not visually, the pixels don't change, but in the motor space in which you're moving the mouse or trackball on the desk, the target's actually magnified, which is kind of cool. Why isn't this just as good as dropping the gain? Because then you've magnified the motor space for your entire screen, including all the space between targets, right? Which commonly would be felt as, oh, the mouse is just too sluggish. So this is magnifying targets in motor space based on the angular deviation of the user's movement. And we can measure that spread and adapt the gain. So let's take a quick look here.
Using a mouse or trackball consists of two primary steps. First, an initial or ballistic movement moves the mouse pointer in the general area of the target to be selected, while a second, corrective movement moves the pointer directly onto the target. Many people with motor impairments are able to perform the first step well, but have difficulty performing the second, corrective step due to the amount of motor precision required. One solution to this problem is to slow down the mouse cursor when it approaches the target, much as a car slows down when driving down an icy road. However, it's difficult to know what the user intends to point at, and thus the cursor may be slowed down by unintended targets. A key insight of the angle mouse is to use the movement of the mouse, and in particular the angular movement of the mouse, to slow down the mouse pointer only when the user is near their target. In this video, the angle of mouse movement is shown on the screen as a gray dotted line. The angle of movement remains relatively consistent while the user moves toward the target, but spreads out considerably when the user begins to focus in on the target. The angle mouse uses this change in angles to slow down the mouse and to enable the user to more accurately select the target. Thus, the angle mouse works similarly to a race car, moving quickly on the straightaways and slowing down to handle the curves. To evaluate the effectiveness of the non-impaired with motor.
All right. Just some quick results to show you this actually works. So the movement time was reduced and the errors were reduced. If you know what Fitt's law is, there's a measure from Fitt's law called throughput, which is a combined speed accuracy measure. So given that speed was better and errors were better, it's not a surprise that we have a significant improvement in throughput by about 10%. The mouse is a very optimized thing. It's been around a long time. It's actually really hard to run a study and get a win changing anything about the mouse. If you go just change the mouse in some way, it's going to be worse. So getting a win was very nice. Also, what was nice is there was no difference, no detectable difference for people without motor impairments. So essentially, we could all have the angle mouse, and you'd be just fine. And if you need it, it would help. And if you don't need it, it wouldn't hurt. So that's nice. Another project, which was devoted more to touch, was called Smart Touch. And Smart Touch observed that people touched tabletop interactive displays in a variety of ways. And if they have certain motor impairments or motor disabilities, they often touch the screen in different ways, including not always with the ability assumption of a single finger that lands and lifts, without sliding and so on from a single point. And so Smart Touch said, can we just let people touch the screen however they want, and the screen, the software, will figure out the point they intended? What a concept. Touch how you like, touch however you like. That was the goal. So Smart Touch did this through a template matching process. It captured templates in the form of touch against a series of training tasks where there's a crosshairs that the user would touch. And then we did a point cloud matching process based on the Hungarian correspondence algorithm to essentially at runtime allow the user to touch however they want and find out the touch point that they intended. And I apologize, this is the one video that for some reason I can't get subtitles on with YouTube.
Although touch input has been widely adopted, it remains largely inaccessible for many people with motor impairing disabilities such as cerebral palsy and muscular dystrophy. To improve upon the limitations of touchscreens, we created Smart Touch, a novel 3-step algorithm capable of mapping any number of arbitrary contact areas to a user's intended XY touch location. First, Smart Touch analyzes a user's touch process to extract the most relevant touch data. Second, the extracted touch data is compared to previously observed touch templates. Third, the location of the user's intended touch point is predicted by leveraging information stored in the best match template. Smart Touch was designed to accommodate 2 observed behaviors. First, not all users possess the dexterity to fully extend a single finger. Instead, users may impact the screen with multiple fingers, their knuckles, or with a closed fist. All of these touch behaviors create multiple touch instances, although only a single touch is intended. Second, users had difficulty landing and lifting near their intended target. In order to compensate, participants went through an extended touch process where the screen was used to provide stability and support as participants attempted to acquire their target.
So remember, just touch the screen is not so just for many people, and for all of us in particular if we're in certain situations, right? So Smart Touch reduced the distance from the intended touch point by about 3 times. So it was a big win compared to the native touch down or lift off techniques, which were how most touchscreens operate. Now remember, the vision of ability-based design talked about situated abilities. So let's look at some projects that dealt with situational impairments. Walk Type was a really nice project led by Anhong Guo, who's at Carnegie Mellon and has been for a few years now. And our observation was, well, it's hard to type on a smartphone while walking. And so Walk Type reduced the errors through a key press classification process by about half. So we could actually make you twice as accurate while you're typing while walking. So how do we do that? So we gathered a bunch of training data from 16 participants, around 50,000 key presses, as well as 3-axis accelerometer data, and things like the touch down, touch lift, travel time, if the user slid during touching, and so on. We did not use the gyroscope on devices. They were not very well developed back in 2010 and 11 when we did the work, so we relied just on the 3-axis accelerometers. I think the models would even improve more with the gyroscope. So what were the models? Well, the baseline model is just the key bounds, right? That's just hit testing, basic key bounds. And so while walking, people are about 72.8% accurate in our model. And then we expanded the model to take the touch data like touch up, touch travel, and the time between taps, along with the phone's motion itself, because as you walk, the phone's moving, and we can detect that from the accelerometers. And so we looked at the vertical direction at each tap, the vertical displacement of the phone at each tap. And then also we could look at the acceleration by sampling the time, the acceleration between successive taps. So we would resample that acceleration and get 10 readings from that. And that resulted in a model that was 94% accurate. The touch-only model is about 91%. So we get a bit extra from the accelerometer data is essentially what that's adding. And then there was yet one more step, which is actually the most interesting. We could tell which foot was hitting the ground when, as you walk. So it turns out when you step forward with your left foot, you rotate your phone slightly to the right. And when you step forward with your right foot, you rotate your phone slightly to the left. It's just a little bit, but it's enough we could detect it. And so because of that, we knew that there was rotation going on with your thumbs or fingers while you strike the keyboard. So we called that the walking pattern model, and we could actually extract the phase of your gait while you're moving. That brought us to 95.7%. So the final algorithm for Walk Type was that we used the touch anchor at the center of each key. So if you're right dead in the center of the key, then that overrides everything. But if you're off a little bit, we have a vote from each of those models, and the majority would rule. If all 3 votes said a different key was pressed, then the walking pattern model would win because it was the most accurate. The final classification accuracy with this model was 97.3%. Okay, so that's a model, but now, especially in HCI, we want to know, well, does this actually help in practice, like while you're walking? So we ran a study with new participants, and it was a controlled keyboard, which is just hit testing versus the walk type model, the walk type algorithm. And we also tested people sitting and walking. They entered 30 phrases each, and we collected almost 60,000 key presses. So does it work? Well, what we found is that while sitting, people were not any faster in terms of words per minute between the control and walk type. They were a little faster on average, but that's not significant. But while they're walking, we did in fact find about a 12 or 13% gain in words per minute while walking. So 13% win in text entry speed while walking is pretty nice. And then on top of that, we found that the error rate went down significantly in both conditions. So while sitting and while walking, especially while walking, we dropped the error rate by almost half. So that's a significant improvement to text entry while walking. Another nice result was that participants, this is invisible, right? Participants didn't see any difference. They didn't know which conditions they were in. It was a within-subject study, so they did both, but they didn't know. They just typed. And then we'd ask them, which condition did they prefer, and 14 of 16 picked walk type without knowing that walk type was there. So that was a nice validation point as well. Another situational impairment. How many of you have been reading like a news article or New York Times or something, and you look away, because remember we're interacting in 4-second bursts, and then you look back at the screen and it takes you 3 of those 4 seconds to figure out where you left off? Often we go back to the top because that's kind of an edge, maybe a reference point. So you're always jumping back up. We've all had that experience. You kind of reread what you saw. It's annoying and it takes time, and that time's precious because, again, we only have 4 seconds as we interact. So Switchback was trying to remedy this by using the front-facing camera to look at people's eyes and to help them resume reading where they left off. So as you're reading, it's tracking your saccades. And so let's say you're reading this beautiful Latin text, and then you look away. You look away from the screen, and then you look back. Switchback will actually apply a highlight. You don't interact. You don't do anything. It just applies the highlight when you return your gaze. It's there for a moment, and then as it sees you begin to read again, the highlight fades out. So it's a very nice kind of ambient interaction. I'll skip the video just for the sake of time. But we use the front-facing camera to detect the face and find the eyes. This is just a commodity smartphone. There's no special, eye-tracking apparatus here. And what we could do then is follow your gaze as you read. We smoothed that, and we could basically pull out the saccades. Where are your eyes flitting back and forth across the line, so we know where you are in the reading process. And for the study, we had people walking on a treadmill. It's a little dangerous to do this study out on the street with cars and stuff. So we had the people in a lab. We had 17 participants and a within-subjects design that involved standing versus walking, and a distraction task versus a no distraction task, and then a control condition without switchback and switchback. The distraction task was shown on a monitor off to the side. You can see here in this diagram. And it was a distraction task taken from those highly abusive psychologists who do things like this to people, where they show a rotated field of T's and L's and make you count the L's. It's even hard to do in my diagram. So this was the task they had to do. So clearly they had to look away and even attend elsewhere and really focus and then look back. So that was the distraction task, those psychologists. So what happened? So reading speed in the no distraction task, there was no difference, right? Because they never had to look away, so we wouldn't expect a difference. But in the distraction task, we improved about 8% faster, which was 19 words per minute reading speed. That's a reasonably good win there with switchback. And then I'll mention also, we did have a comprehension task as well to make sure that they knew what they read. Otherwise, they're just glancing over words, right? So they actually had to understand what they were reading. Okay, last one, a current project that I'm working on, which is underway. And we call this the Ability-Based Design Mobile Toolkit. And it's an app developer's toolkit. So we have a developer on one side, the user on the other of this diagram. And in between is this toolkit, which I'll start in the middle, has a series of observers, which could be extended to observe any any kind of behavior. Right here I have touch observer, gesture observer, and an activity observer for things like walking, running, sitting, standing, driving, that kind of activity, bicycling. And the observers watch the user's activity at runtime. So this is runtime without a task model. Like Supple had the task model where you perform in the test bed. There's no test bed here. It's just observing behavior at runtime. And then the ability modeler integrates across these observers. So we can ask things like, are they walking and are they exhibiting signs of tremor while they walk? And if that's true, then do the following with the UI adapter to the UI. Like make certain widgets marked as important bigger and ones that are less important smaller, that kind of thing. So we built a series of exemplar applications from keyboards that expand automatically as you try to log in if you're having trouble because you're missing keys. This is a Pokemon Go kind of reproduction where if it's too hard to swipe and throw the ball at the Pokemon gets closer because it's detecting that you're doing it with like one thumb and you can't reach the full extent of the screen. The running application is if you're running and you get a notification, let's say your iPhone's in a sleeve on your arm, you might have seen people do that, and you need to be able to dismiss the message or read the message, it'll expand the text because it knows you're running, and it'll expand the button so you can dismiss it more easily. Or the fat finger problem. So if you're typing on a keyboard whose keys seem too small for the size of your fingers, it will begin to expand both the text so that you can place the cursor more appropriately.
Conceptual.
All right, I'll skip the video. I was going to show some code, but the upshot of this, because who wants to read this really, is you can just, this is an Android, you just extend the main activity with our activity, which is the ability-based design library, and then with a couple lines of code, you get access to all of this. This is just how you set up your project with the modeler and the UI adapter. And then on the client side for the applications, you can do things like, does it seem that the user has tremor? If so, make sure that there's a minimum size of certain widgets. Or is the user running? Then only show the important widgets while they're running. Or do they seem to exhibit tremor while walking? If so, resize the fonts to be bigger. And if they're not anymore, if they stop running or walking, then revert the UI back to its normal size. So in a few lines of code, we can get some really powerful adaptations. Okay, so a vision for the future. A project that I'm beginning to work on, and I'd love your thoughts, and we can talk about, is the notion of an ability profile. So let's say someone approaches any number of devices, laptops, phones, websites, kiosks, ATMs, input devices of various kinds. Could they have something that identifies themselves to these devices, to these technologies, and the technologies say, I know something now about your abilities. Not because there's anything specific to these devices, but because there's this more general notion of an ability profile. That the profile encodes something application agnostic about the user. And maybe that allows the system to pull down, say from the cloud, a profile that then these systems use. They have an ability engine that then adapts themselves according to what the user prefers, what the user can do. Imagine if all of our systems and devices knew something about us and could respond to us in this way. Now, obviously, there's a lot of privacy and security concerns here, and so we'd have to work at all that out. But from an end-user interaction point of view, I think this is a very exciting idea. I'm not the only one who's had a vision similar to this. Greg Vanderheiden, who ran the Trace Center at Wisconsin and then Maryland for many, many years, also talks about something he calls the global public inclusive infrastructure that has a sort of similar idea, and we've been talking about that for years. Okay, let's zoom back out and wrap up here. So what is the ability-based design process really that we've seen in all these projects? The first step is that we observe a user's behavior, right? There's some observation of the user's behavior. So you can see in these thumbnails, you'll be reminded from each project whether it was in a confined test bed like Supple, or the angle mouse, we're just observing how people move when they're pointing, or we're observing where people are looking and switch back, or how they're typing and walk type. We're observing the behavior. The second step is that we do something to measure or model that behavior, right? We create some kind of model of that behavior. And so that's often can be as complicated as certain forms of signal processing and model building. It can be as simple as just calculating angular deviation while the mouse moves. but somehow we are measuring and modeling and kind of reasoning about that behavior. And then we're responding to make that user's behavior more successful. We're highlighting text in switchback. We're classifying key presses to be more accurate in walk type. We're generating custom interfaces in supple. We're dropping the gain at the right time in angle mouse. We're matching through a point cloud algorithm in smart touch, and so on. So that's a pretty standard kind of AI agent in the world process, right? And so maybe no surprise there, but that's really the overall kind of ability-based design process. And then, of course, at the end of this, we have to iterate, because after responding to make the user more successful, we need to observe that they're actually more successful and hopefully continue the process. If they're less successful, then maybe we need to revert, right? So how can AI help? Well, probably in lots of ways, and you guys might have better ideas for that than I do. But it seems to me that in the observing of users' behavior, we need to get the right data. And I put the right data in quotes because what the right data is kind of depends on what we do with it. But we want the right data at the right granularity so that we can make the right models in step 2. We can measure the right things and then take the right action in step 3. So in step 2, one of the big things that I think AI could help with is understanding users' intentions, which is really hard in certain cases. We can observe what they do, and we can make a model of what they're doing, but what are they trying to do? That would be far more valuable. What are they trying to do? So, in supple, we tell them what they're trying to do. Or in smart touch, we tell them what they're trying to do. Touch the crosshairs, point to the circle, we'll make a model, right? But it has to then be a separate process from the runtime experience. It's like a testbed experience. And so we get more to a runtime experience with things like switchback or the angle mouse. And then third, respond to make that user's behavior more successful. Well, we need to respond in the most effective ways, which is obviously situationally dependent and task dependent and goal dependent. But if we know the user's intention, then we can know something more about what's the most effective way. This sounds pretty intelligent to me. So you guys solve that, please. I've been working on inferring intention for a long time. Actually, this is a paper from 2012. It's just a quick mention. It's called The Input Observer. And we actually had, without any task model, the ability to measure text entry performance metrics like speed and errors, and pointing performance metrics just from observing people's everyday use of their computers in the background. Of course, they gave us permission to do this. And we combined things like crowdsourcing and unsupervised clustering algorithms, and we searched the web for spelling things and so on. So it was kind of an involved process, but you can get intention. Now this is for text entry and pointing, which on the one hand are simple tasks, on the other hand can get complicated too. But we were getting at users' intention in this way. We still had to have some humans in the loop, though, through crowdsourcing. All right, so what are some challenges with all this? There are plenty, but a few are sensing and modeling a user's abilities, obviously still very challenging. Inferring a user's intentions, as I just mentioned. Adapting in the right ways and knowing what those are. Defining and scoping ability profiles. The scope of those could be almost infinite, so we have to find a way to get our arms around that. Often we want to do things in accessibility that are best done at the OS level. Accessibility and security are both kind of like the things that, Clayton Lewis, I think, who said accessibility is like the computing's greatest hack. Like you're always trying to do stuff to make the system do things it doesn't want to do because of security issues, right? So if we can get buy-in at the OS level, we can do things like adapt interfaces in ways that if we just do it application by application, sometimes we can't get as deep as we need. And then I mentioned, of course, privacy and security concerns. If you want to know more about ability-based design, I'd point you to the CACM article we had a few years back. This is the issue and the cover. Maybe you saw it go by. And so you'll find it there. There's a few other things, of course, too. One from 2011 that was earlier. And with that, I will finish. Thank you very much for your attention.
All right, so we'll have time for a few questions. All right, so please raise your hand and I will give you the mic.
Hi, thank you very much for the talk. I just had a question on the, I think the touch template part. So are there a finite set of templates that you're trying to match the user to? Or are you like, or is it more of a continuous space?
Yeah, so we had we showed crosshairs on the screen, and so those would, well, let me back up. We first allowed the user to define their reachable space, so they could kind of outline their space, which is an important step in a project like this, because not everyone can reach in the same extent. And within that space then, we showed a random location of a crosshairs. And as you saw in the video, we let people then touch the crosshairs however they wanted. So sometimes they'd swipe, sometimes they'd move around quite a lot, and so on. We then, from that, you can imagine the input generated in that process, so there's a series over time. We extracted what we thought were the kind of keyframes of that touch. So that gets a little bit in the weeds, but there's a way to pull out what you think is probably the most indicative kind of capture of that touch. And it'll often have multiple ovals in it. So the touching, as you saw on the screen perhaps, were abstractions of ovals. We weren't getting the raw capacitive image. We were getting ovals that the system reported. Then that was saved as a template. So we knew where the ovals were, and we knew where the crosshairs is. And what we found through our experimentation was that if we saved about 30 templates per person, we got the best performance. So each person would generate 30 templates, which really doesn't take very long. I mean, it's just a crosshairs, right? So it's a quick task. And then at runtime, when they go to touch a button or something, we take their touch and we do a matching process to that 30 set of templates, find the one that matches best, use that offset to then figure out where they're intending. Does that make sense?
Yeah, thank you.
This is just a template matching process. The cool part was the point cloud matching process made it very flexible to figure out which template was really best. That was a nice use of that.
I have two questions, so I'll just put it out there. You can answer one or both. So the first question is this. So you showed, so most of our traditional interface is finger-based or hand-based, and you show integration with two Gs. One is gate, the other one is gaze. Yeah. So my question is this: we are all human beings. We use many modalities to interact. I'll take up one example: speech. We can speak into things, okay? And the error rates. Now I'm quoting some experiment we did a long time ago in the beginning of the genomics. People used to physically type in ADDC and look at their page and type in ADDC. And the error rates were humongous. But if they just spoke ADDC, error rates was much smaller. Can you take fingers out of the equation or finger-like devices out of the equation and bring in speech and other things? Question number one. Number two, I'm a biased human being. My native tongue is not English. I'm from the southern tip of India. I speak a wonderful language called Malayalam, grammatically correct to the Sanskrit language, phonetically complete vocabulary, and I can assure you there are many Mandarin speakers in this audience. So we are wondering, how much harm has QWERTY keyboard and English language done to this world? Can you correct? There are other people, in the world that speak other languages, and nowadays it's easy to map from stupid English to other more conversational languages.
Sure.
I'm sorry.
Yeah, well, I'll take the second question first, I guess. This might be better to expand on in the hallway, and so I'm happy to talk more.
Yeah, no, I'll be here. We can talk.
Yeah, that's fine. I'm not sure I don't know that that's an ability-based design specific question, because we could have keyboards in, like the European keyboards, the Azerty layout, and there's other layouts. QWERTYnomics has a lot to say about this, right? So we've been stuck on QWERTY because we got stuck on QWERTY because we got stuck on QWERTY, and back to the Scholz and Glidden keyboard when the typewriter was first invented. I actually did I helped a student with a course paper. He was a Mandarin speaker, and it was called Language Imperialism. And it was about how English and text entry research in particular in our conferences, at least the ones I go to, are always in English, which is really a shame, right? Because we're missing out on the diversity of language and the diversity of evaluation of other technologies. So I think that's real. I'm agreeing with you there. And in a way, it is ability related, right? Because your ability to read or speak in one language may be different than others and so on. As far as the first question around speech, yeah, so we have a paper actually that I did with a couple of colleagues at Stanford about how we actually met. It'd been a long time actually since speech versus typing on a mobile like smartphone, had been measured. Speech recognition quality back in the 90s was not very good, but now it's around and it hadn't really been studied. And we found it was about 3 times faster than typing on a keyboard. But the usual caveats apply. So manual input is not going to go away because speech is not always appropriate, right? So someone's typing right now somewhere in this room and they're not talking. Why? Because it would be disruptive, right? So there's lots of contexts in which we're not going to use speech. But I do think we're going to continue to see its increase. And it is much faster. And the recognition rates have gotten much better.
Can people speak and click at the same time?
Speak and they don't use the same brain centers, so I think so, but I haven't formally seen any study of that in a rigorous way. Yeah. You can't speak and listen at the same time very well. That's the same neurological center.
So since I have the mic, I will ask the last question before we go into a shorter coffee break. So ability-based design depends a lot on the context. And in the projects you show, they are mostly about the individual user's context. So how do you think this generalize or extend to a more collaborative setting where there's also a diverse range of human abilities in play?
Yeah, that's a great question. Thanks for that. And that wasn't, we didn't arrange that ahead of time, but I love that question. You're right. So all the examples I showed were individual user, kind of individual HCI types of projects, and not taking into account like social context is maybe the way I'd phrase. And we know that when it comes to accessibility, there's a lot of social context that matters. People, rely on allies to help them in certain ways. Allies, step forward and partner with others and their friends and so on. So there's a kind of ecosystem that's beyond physical context or kind of environmental context, which I showed, to expand to more the human context and the social context. So all I can say is that's a great direction for future work. What are we going to do in it? Do you want to collaborate?
All right, so let's thank Jake once again.